In the early morning of July 1st, 2025, a telescope in Chile detected something extraordinary, a point of light moving through space at a speed impossible for any object from our solar system. It was 3I/Atlas, the third confirmed interstellar visitor in the history of astronomy. And when scientists began studying it, they discovered that this comet didn't resemble anything we had seen before. Its chemical composition was so extreme, so far out of the ordinary, that it forced astronomers to reconsider everything they thought they knew about comet formation in other stellar systems. Now, months after its perihelion passage on October 30th, 2025, the data collected by the world's most advanced telescopes are revealing a story even more fascinating than anyone anticipated. A story about exotic chemistry, cosmic radiation, and the secrets held by interstellar space. But before diving into the mysteries of 3I/Atlas, we need to understand something fundamental. Interstellar objects are extraordinarily rare. Throughout the entire history of modern astronomy, we've only confirmed 3 visitors that definitively come from beyond our solar system. 3. In centuries of observing the cosmos. The first was Oumuamua in 2017, a cigar-shaped object that mysteriously accelerated as it moved away from the Sun. The second was 2I/Borisov in 2019, a comet that at least behaved more conventionally, though with unusually high levels of carbon monoxide. And now we have 3I/Atlas. The difference is that 3I/Atlas has turned out to be the strangest of all, the discovery of an impossible visitor. When the Atlas Telescope System, Asteroid Terrestrial Impact Last Alert System in Rio Hurtado, Chile, detected this object on July 1st, 2025, astronomers immediately noticed something didn't add up. Its orbit was completely hyperbolic, with an eccentricity of 6.14, which in simple terms means this object isn't orbiting the Sun. It's passing through our solar system like a bullet fired from the depths of interstellar space. Its speed is dizzying, approximately 58 kilometers per second relative to the Sun, equivalent to about 208,000 kilometers per hour. To put that in perspective, at that speed, you could circle the Earth in just over 11 minutes. It's so fast that it vastly exceeds the solar system's escape velocity, which means that after its encounter with the Sun, 3I/Atlas will shoot back out into interstellar space, and we'll never see it again. We had one single chance to study it, an extremely limited time window to unravel its secrets. But the speed, as impressive as it is, isn't even remotely the strangest thing about 3I/Atlas. In the days following the discovery, observations from the Nordic Optical Telescope and the Tidy Observatory in the Canary Islands confirmed that the object was clearly active, showing a diffuse coma of gas and dust. It was definitely a comet, but when spectroscopes began analyzing the light reflected and emitted by the object, scientists were stunned. Initial data showed that 3I/Atlas was already active when it was 6.4 astronomical units from the Sun, a distance where normal comets are completely frozen and inert. Something was sublimating from its surface at extremely low temperatures, and that something wasn't water. Observations from the Transiting Exoplanet Survey satellite, TESS, revealed that the comet had been bright and active since May 2025, well before its official discovery. This suggested the presence of hypervolatile ices, compounds that evaporate at much lower temperatures than water. The prime candidates were carbon dioxide and carbon monoxide. The question was, exactly how much of these compounds did it contain? On August 6, 2025, the James Webb Space Telescope pointed its powerful NIR-SPEC infrared spectrograph at 3I/Atlas. What it saw left the scientific community speechless. The comet was emitting carbon dioxide in massive quantities. But not only that, the ratio of CO2 to water was 7.6 to 1. For every water molecule, there were more than 7 carbon dioxide molecules. To understand how extraordinary this is, you need to know that in typical comets from our solar system, water dominates completely. Most comets have CO2 to H2O ratios of less than 0.5. Even the most CO2-rich comets rarely exceed a ratio of 2 or 3. A ratio of 7.6 is statistically 4.5 standard deviations above the trend observed in long-period and Jupiter family comets. In scientific terms, this is extraordinarily anomalous. It's like finding a 4-meter-tall human. Technically possible, but so rare, it defies all probability. No comet in our solar system has this composition. None. Exotic chemistry and cosmic radiation. Scientists began formulating theories to explain this impossible chemistry. Perhaps 3I/Atlas formed very close to the CO2 ice line in its original stellar system, a region of the protoplanetary disk where carbon dioxide condenses but water still remains gaseous. Perhaps it comes from a system with different metallicity than the Sun. Perhaps it experienced chemical processes during planetary formation that are completely foreign to those that occurred in our solar system. But there was a problem with all these explanations. They didn't simultaneously explain the high levels of CO2 and the substantial levels of CO that were also detected. Protoplanetary disk chemical evolution models struggled to reproduce both features at once. Then scientists began considering another possibility, more intriguing: cosmic ray processing. For millions, perhaps billions of years wandering through interstellar space, 3I/Atlas was exposed to galactic cosmic rays, high-energy particles traveling through the galaxy at speeds close to that of light. These cosmic rays can penetrate the first 15 to 20 meters of a cometary nucleus and chemically alter the ice. Laboratory experiments have demonstrated that when cosmic rays strike ice containing water and carbon monoxide, they can convert CO into CO2 through radiation-induced chemical reactions. With sufficient time, this irradiation can create a carbon dioxide-rich crust that coats a more pristine interior. A scientific study published in October 2025 proposes exactly this: that 3I/Atlas is better understood as a natural laboratory for cosmic ray processing than as a direct messenger from a distant protoplanetary disk. The comet has an irradiated nucleus stratigraphy with a cosmic ray-processed crust coating a pristine interior protected from radiation. This interpretation is revolutionary. It means that what we're observing isn't necessarily the original chemistry of the system where 3I/Atlas formed, but rather the result of billions of years of chemical alteration in the vacuum of interstellar space. The extreme CO2/H2O ratio reflects processing efficiency, not formation conditions. The substantial CO levels indicate ongoing chemical evolution, not pristine composition. But there were other anomalies that captured scientists' attention. Early observations of the comet showed strong nickel emissions but weak iron emissions, an unusual ratio because these two metals typically appear together in solar proportions in comets. As 3I/Atlas approached the Sun, this ratio began to normalize, suggesting temperature-dependent release of these metals or differences in the chemical pathways that formed their original ices. The comet's coma also displayed a distinctive reddish color, similar to extreme trans-Neptunian objects. This reddish hue is indicative of complex, irradiated organic compounds, complex carbons that have been altered by radiation for eons in deep space. The Perihelion passage, a cosmic examination. On October 30, 2025, 3I/Atlas reached its perihelion, the point of closest approach to the Sun, passing at approximately 1.4 astronomical units from our star, just inside Mars's orbit. At that distance, the temperature on its surface reached hundreds of degrees Celsius. The solar radiation was intense. It was the moment of truth. Perihelion functioned as a cosmic final exam. If 3I/Atlas was a comet with exotic composition but conventional structure, the extreme heat should cause massive outgassing. We should see an explosion of cometary activity, with jets of gas and dust erupting from its surface. Its brightness should increase dramatically, and that's exactly what happened. Observations confirmed a phase of intense outgassing shortly after perihelion. The comet survived intact. It didn't fragment, indicating it has a relatively cohesive internal structure despite its exotic composition. The world's most powerful telescopes were pointed at 3I/Atlas during this critical period. The Hubble Space Telescope captured detailed images of its coma on July 21st and then again on November 30th, 2025, allowing astronomers to estimate that the nucleus diameter is less than 5.6 kilometers, possibly as small as 440 meters. The James Webb Space Telescope performed spectroscopy before and after perihelion. The SphereX mission collected data for a full week in August, but perhaps the most unique observations came from unexpected places. 3 NASA spacecraft at Mars, MAVEN, Mars Reconnaissance Orbiter, and the Perseverance rover, captured images of the comet from a distance of approximately 30 million kilometers in late September and early October. MAVEN's ultraviolet instrument was able to detect the halo of hydrogen atoms surrounding the comet, providing information about how water breaks down into hydrogen and oxygen under solar radiation. And in November, when the comet was behind the Sun from Earth's perspective and impossible to observe with ground-based telescopes, NASA's Europa Clipper spacecraft, en route to Jupiter, captured ultraviolet spectroscopic observations of the comet from a unique angle. It could observe both of the comet's tails from between their downstream directions, a perspective no other instrument could achieve at that time. The heliophysics missions Stereo, SOHO, and Punch also observed 3I/Atlas during its passage near the Sun, tracking it when it was invisible from Earth. Even the Lucy and Psyche spacecraft, en route to the Trojan asteroids and asteroid belt respectively, captured images of the interstellar visitor from distances of hundreds of millions of kilometers. It was an unprecedented observation campaign. 12 NASA assets captured data from the comet from locations distributed throughout the solar system, providing a complete three-dimensional view of this visitor from another world. The data collected are invaluable. Measurements from Europa Clipper's ultraviolet spectrograph showed evidence of intense outgassing after perihelion, confirming that 3I/Atlas experienced dramatic changes as it approached the Sun. JWST spectroscopy revealed not only CO2 and H2O, but also carbon monoxide, CO, water ice, dust, and a tentative detection of carbonyl sulfide, OCS, a compound rarely detected in comets. All these observations are painting an increasingly detailed portrait of an object that spent eons traveling through the void between stars, being bombarded by cosmic radiation, accumulating chemical alterations layer by layer, until it was finally gravitationally captured into a trajectory that brought it through our solar system. 3I/Atlas isn't just an exotic comet. It's a chemical archive of interstellar processes we're only beginning to understand. implications, and the future of interstellar astronomy. The existence of 3I/Atlas is teaching us profound lessons about the universe. First, it confirms that interstellar space isn't empty. Objects are constantly crossing from one stellar system to another, silent carriers of information about worlds we can never directly visit. Each interstellar visitor is like a bottle thrown into the cosmic ocean, containing messages about the chemistry, physics, and evolutionary processes of distant stellar systems. Second, it shows us that these visitors aren't as rare as we thought. If we've detected 3 interstellar objects in just 8 years, that statistically suggests there are thousands, perhaps millions of these objects crossing our solar system at any given moment. They're just too small, too dark, too fast for our current telescopes to detect them. We're seeing the tip of the interstellar iceberg. The implications are staggering. If the space between stars is filled with these cosmic travelers, then the exchange of material between stellar systems is a common, constant, universal process. The ingredients of life could be transported from one system to another. Panspermia, the idea that life can spread between planets and even between stellar systems, suddenly seems much less speculative. Third, 3I/Atlas is driving technological advances. Its discovery has demonstrated the need for more advanced space surveillance systems. The Vera C. Rubin Observatory in Chile, which coincidentally captured fortuitous images of 3I/Atlas during its science validation observations in June 2025, will begin full operations soon and is expected to detect dozens of interstellar objects every year. We'll finally have a real statistical sample to study. It has also inspired interception mission proposals. ESA's Comet Interceptor mission, currently in development, is specifically designed to rendezvous with interstellar objects or pristine Oort cloud comets. The idea is to have a spacecraft on standby, ready to launch and intercept interstellar objects when they're detected, studying them up close, taking samples, perhaps even bringing material back to Earth. It would be cosmic archaeology in real time, studying natural artifacts from alien stellar systems without having to travel light years away. But perhaps the most profound lesson 3I/Atlas is teaching us is about scientific humility. Every time we think we understand the rules, the universe shows us exceptions that challenge everything we thought we knew. We thought we knew the typical chemistry of comets. 3I/Atlas proved us wrong. We thought interstellar objects would be exotic, but recognizable versions of objects from our solar system. Oumuamua, Borisov, and now 3I/Atlas have shown us that each visitor can be completely unique. The universe is infinitely stranger, more complex, more wonderful than our minds can conceive. And each interstellar visitor we detect reminds us of this. 3I/Atlas is now on its way out of the solar system, moving away at speeds that will carry it back into interstellar space. By December 2025, it will be barely visible with the most powerful telescopes. By 2026, it will have completely disappeared from our view, lost in the vastness of space between the stars. But the data it left behind will continue to be analyzed for years. Each spectrum, each image, each measurement contains clues about processes occurring on timescales of billions of years and distances of light years. Scientists are only beginning to unravel the stories 3I/Atlas has to tell. And somewhere in deep space, there are probably dozens, hundreds, thousands of other interstellar objects approaching our solar system at this very moment. Objects with even more exotic chemistries, with even stranger histories, with secrets we can barely imagine. The question isn't whether we'll detect more interstellar visitors. The question is when and what they'll reveal about the mysteries waiting between the stars. Do you think 3I/Atlas was processed by cosmic rays for billions of years, or does its extreme chemistry reflect unique formation conditions in its original stellar system? Leave me your theory in the comments.